Hello, everyone. Welcome to this week's episode of Howdy Partner. The Howdy Partner show is a weekly tweet series where we highlight AWS Partner Network partners who have built innovative solutions and they are validated by us, Partner Solutions Architect. My name is Nneoma Okoroafor. I am a Partner Solutions Architect with AWS with the Scale COE team. And what we do is to help AWS partners with their technical validations. On my end, I'm focused on partners in AI, ML, generative AI to help them with their journey along the AWS Partner Network. And with me, I have my colleague Kruthi. Kruthi, do you want to introduce yourself?
Yeah, thanks, Nneoma. Hi, everyone. I'm Kruthi, and I'm also a Partner Solutions Architect. I'm on the same team as Nneoma. And like Nneoma mentioned, I do help partners in doing their technical validations and partner discovery calls. And I primarily focus on long-tail ISV partners, specifically in the AI/ML and the GenAI space. And I'm based out of San Francisco. Everybody on the chat, feel free to let us know where you're based out of. And I'll hand over to Perminder.
Thank you, Kruthi. Myself, Perminder Singh. I think some of you have probably seen me last year doing some of the quantum computing sessions in this Twitch show. I'm based out of Dallas. I take care of the quantum partners at AWS. I help them build solutions on quantum chemistry or optimization and validate those solutions. And as well, I work with some of the DSI partner in this space too. And today we will be this session will be joined by Mike at MathWorks, and we will be talking about how Matlab can be used to quantum computing program, which can be written in Matlab, and how you can use Amazon Bracket using SDK. With that, why don't we invite Mike Kruthi?
Sure.
Hey.
Hi, Mike. Do you want to give a quick introduction of yourself and what you'll be talking to us about today?
Yep. Hi. So I'm Mike Croucher. I'm from the MathWorks, the makers of Matlab and Simulink. And I'm here today to talk about Matlab and Simulink in general, but also about some of the new quantum computing functionality that we've added in recent years. So I met some of you guys at the SC conference in late last year and was working over at your booth showing off our new quantum technology. And so that's how we met, and we talk about quantum computing and Matlab in general. So hi.
Yeah, supercomputing is the premier event, right? A premier conference in the high performance computing, and we have been participating in that event from a couple of years now. And what we thought from the quantum side in that was like from 2022 and 2023 at Dallas and the event in Colorado, we thought like, why don't we bring some of our premier partners, ISP and GSI, to showcase their solutions, which they have built with us. And that is where I think you guys also participated last year. And thanks for that. We'll see if we can bring you guys in again in Atlanta this year.
Yep, we'll be there. We'll be there. So no, yeah, MathWorks have been at supercomputing for many years now. So we're a pretty old company actually. It's we've been going for 40 years.
Wow.
This is our 40th anniversary. Will be later this year. So I think to be a tech company for 40 years is pretty good going.
Good. And where is your company main engineering group sits? Like, is it like spread all over the world, or is it specific?
Yeah, I mean, if I can just share my screen a second, like I can show you guys some stuff. So just a little bit of an introduction to Matlab, so and MathWorks and what we do and so on. So our primary products are Matlab and Simulink. That's what we're known for. But we've actually got dozens, I think well over 100 different products. And and some of these are listed here. And if I just give you guys the link, I'll share that with you later so you can send it on to everybody. So, you know, all kinds of different things, including the quantum computing add-on that we'll talk about later today. So the MathWorks then, we're all over the world. So our main offices are in Boston, over in the US. But as you can tell, I don't have an American accent. I've got a British accent. That's because I'm based in the UK office. So the UK office is in Cambridge. But again, I then work remotely. So I'm in Leeds in the UK. So yeah, there's 34 locations around the world. I was about to tell you all that we had 6,000 staff members. It seems I'm slightly out of date. There are now 6,500. We've got over 5 million users. And if you can download our company fact sheet from this website and you know, see things like who our major customers are and our revenue and so on and so forth. But I've been working here now for just over 3.5 years. But I was a customer of MathWorks for well over 20 years before that, because I spent a lot of time working in academia in high performance computing, research software engineering, and that kind of thing. So I'm just going to come out of this and send this link over to you. So there we go. That's yeah. So and you know, that's the background of our company. Should I tell you a little bit, a brief history of how MathWorks came to be? Because I think it's got some relevance to what we're going to be talking about later.
Sure.
So you're going to have to forgive me whenever I then switch to anything. It's taken me a while because I'm not used to my laptop. I usually do things like this from home, where I've got a great setup. I've got a big 49-inch screen and a microphone, and it's brilliant. But I'm actually here in Edinburgh at the moment for a conference, which means that I'm sat in a hotel room on my laptop. So I'm a little bit, feel like a fish out of water. Yeah, so as I said before, MathWorks is coming up to its 40th anniversary. And it was invented 40 years ago by this guy here, Cleve Moeller. Cleve is a legend in linear algebra. If I just bring him up. So there's Cleve. And indeed, actually, when we go, we talked about meeting at the supercomputing conference. When we go to SC, sometimes Cleve comes with us because, you know, he meets lots of his friends. He's friends with people like Jack Dongara, who's another legend in HPC. And whenever Cleve is at the MathWorks booth, we become even more popular than we usually are, because he's a great draw. People love to speak to him and so on. And Matlab started out as just a simple way of teaching linear algebra. So the story is here. I'll send the link so we can go out in the show notes and so on. Cleve wanted to teach linear algebra to people who couldn't program, like computational linear algebra. And back then, if you wanted to do any kind of programming, you had to do it in Fortran, and you had to use libraries such as Limpac and IcePack to do your linear algebra. And Cleve was finding that all of the computer science, dealing with compilers and so on and so forth, was getting in the way of teaching the linear algebra. So he built this tool solely for teaching linear algebra back then, and he called it Matlab. So it's an acronym for the Matrix Laboratory. Wrote it in Fortran, and here you can see all of the commands that were in the original Matlab. That was it. It was just those. But it really took off. People started finding it useful, not just for teaching linear algebra, but people were starting to use it in all kinds of things, things that Cleve said he didn't know, he didn't understand, such as control theory and signal processing. And sooner or later, he partnered with a guy called Jack Little back in 1985. Jack rewrote the Fortran Matlab in C, extended it quite a lot, and released the first version of PC MATLAB. That was in 1985. And it kind of went from there. The control systems toolbox was I think the first toolbox, but I'm not 100% sure. Yeah, so from 1984-85, from this tiny program just for teaching linear algebra, MATLAB's now this massive multi-billion-dollar company that does all kinds of different things. So one of the ways that I try and, my children often ask me, what is it I do, and who do I work for, and so on, and what do they do? And the way that I try, and the short version that I give them was, if you've seen something cool in the news about big engineering and big science, there's a good chance MATLAB was used in it. And here are some of the some examples of the customer stories that we've got public. So you see things like clean power, NASA missions, scrolling down, helping with making oxygen from the Martian atmosphere, all-electric vehicles, planes, self-driving cars. You get the idea, right? So we've got millions of users worldwide. I think we're at 5 million users at the moment, and it's growing year on year. We use in all kinds of different industries, and my particular role is I work helping with academia. So I go around helping people with their teaching and research, and also I write the MATLAB blog, which is, where is the MATLAB blog? There it is. So I write the MATLAB blog, which is sort of the, lots of deep dives and tips and tricks into things. Yeah, if you're interested in some of the details of MATLAB and what's new and so on and so forth, then I suggest you head over there. So yeah, there's a brief introduction to MATLAB and the MathWorks.
Yeah, thank you, Mike. I think that was really great. Just a quick question. Do you have any examples in the EdTech sector you're working on? Any customer stories?
In the EdTech sector?
In the education sector, is that?
Right, sorry.
Yeah.
yeah. I mean, absolutely. I haven't got any queued up.
Okay.
But yeah, we've got many. Did you have something in particular in mind, or?
No, I was just curious if what work you do in that area. If you have any customer stories that you can share publicly, otherwise, it's cool.
I mean, yeah, I've got nothing queued up. We've got a lot of that kind of stuff, and it would be a matter of. I mean, I don't know. Let's see if I search the completely untested. If I search this for, I can't spell education. Let's try in there. Okay, so yeah, we've got some examples here. There's an MIT class using Docker containers for problem sets, for example. Here's another one, introducing deep learning and Internet of Things to first-year engineering students with MATLAB. So yeah, turns out quite a few that we talk about publicly in education. So virtual labs is another one. So actually, that's something that we pivoted to round about COVID. So a big part of teaching engineering is physical laboratories. You go in and you put your hands on things, and you build things and break things and figure out how they work. And when COVID happened, nobody could go on site. And so we used MATLAB, Simulink, and a thing called Simscape that we also developed to build virtual versions of these labs, so people could simulate all of the experiments and get a similar level of learning. So yeah, we do a huge amount of stuff in these kind of spaces.
Okay, I have a question regarding use cases. Do you have like a particular use case where that is surprising to you, that you didn't think that MATLAB would be like a good tool for that?
Oh, that is a good question, and No, it's well, the reason is because it's like I don't know. It's not that I'm surprised that MATLAB was used. Sometimes it's just like you know, what has been done is really cool, and it doesn't surprise me that MATLAB was used in it. So there's one that I used in presentations quite a few times, and it was the let me see, is it the what's the NASA probe called? Parker, the Parker probe. Yeah, the Parker Solar Probe. So there was a thing in the news, I think a couple of years ago, where it was talking about a solar probe that went really close to the sun, and they sort of had this very poetic way of describing it, where they said it's the closest that humanity has ever got to kissing the sun. And I remember that I just loved this story, and it turned out that our tools had been used in various subsystems to build the guidance system or whatever. I can't remember the details, but it's just like when this then came on TV, and my family, I guess all geeks have this, right? Your family have no idea what you do. It's like vaguely something to do with computers. He mentions MATLAB a lot, whatever that is, and you know that came on the TV, and I could sort of like nudge my kids and say, see that, we were involved in that, in the sense that our tools were used to build it. So I sort of think that's really cool.
Yeah, that's a really good example. Speaking about tools, do you want to start talking about the different tools you use on MATLAB?
Yeah. So the primary. If I again, if I share my screen, then share the screen. So the primary product is this. It's desktop MATLAB. So it's an application that runs on my desktop. It's a programming language. It's a authoring system. It's a way of doing data science. So, for example, I can set up like a notebook environment like this. I can start typing commands. As I type the commands, I get all kinds of contextual help, as you would expect. So I don't know. Let's go from 2 times pi. Oops. Sine x. And then that's very simple. Plot x, comma y. There we go. Let's bring that plot in line. So it's a programming language. It's a way of doing engineering and so on. But I can also then very quickly make a little application out of this. So I'm just going to bring in this extra parameter f inside my sine function. Let's set f equals to 1 to start off with. Nothing new there. But then if I highlight this variable, I can convert that to a numeric slider. And now I've built a simple interactive version of the plot where I can change that variable with the slider. And then if I then hide the code, then I could send this to someone and say, there you go, that's the relationship I was talking about, go and play with it. So, you can very quickly start investigating mathematics. You start programming straight away, get straight into the maths, and you don't have to worry about complex details too much. You can just get started straight away. So MATLAB, then it's yeah. This is our primary product, then the MATLAB desktop. And then along with this, though, are a whole bunch of toolboxes. So, because that's obviously very basic, what I showed you there. But if you go into the documentation, you'll see here that depending on the kind of things you're interested in, parallel computing, which maybe we'll talk about later, AI, data science and statistics, signal processing, image processing, to detailed stuff, engineering stuff like radar, wireless communications. I've not got everything installed on this machine, but you've also got things like satellite communications and wavelets and all kinds of stuff. So this desktop product is our main thing, and yeah, that's what Matlab is in a nutshell.
Okay, cool. So I remember, I remember Matlab as far back as in university, and then see people like engineering students use it a lot, and then getting into machine learning and AI, we get into notebooks, NumPy. So why do you think we should keep on using Matlab?
Okay. Well, so you mentioned, for example, notebooks and NumPy and so on and so forth. So first of all, if I can, where's my web browser gone? There we go. The first thing that I want to point out is you can, if you prefer Jupyter, for example, we have a Jupyter kernel. The announcement for that release was on the Matlab blog. So if you're into Jupyter, you can use Matlab inside Jupyter. If you're a Python user already and you want, and you can use you can run Python inside Matlab. You can run Matlab inside Python. You can automatically convert between NumPy arrays and Python arrays completely seamlessly, and so on and so forth. And I think that so you can use, and people do use both of these tools at the same time. And I think that Matlab really shows its strength when you're doing any kind of computation that is eventually going to be into some kind of engineered system. So when I showed you all of these, let's go to these, some of these customer success stories, for example, here, a lot of these are involved in doing something physical, right? Machine learning isn't just in a live script or a notebook. It's in, in a car, in a plane, in a space probe, in a, what else have we got? An autonomous pediatric exoskeleton, So it's that intersection, I think, of engineering and computation is where our sweet spot is. But of course, we've got a lot of other strengths as well. So, for example, we used a huge amount in industry because we've got code generation capabilities. So you can write MATLAB code, and from the MATLAB code, it will generate C and C++ code. So it's an add-on called MATLAB Coder. And very often, when you actually then deploy algorithms into physical things, it's via this mechanism. And we've got all kinds of tools that then wrap around this for things like safety certification and doing engineering. So if you want to do computational engineering, then I think MATLAB is pretty much the best environment to do it in. Did that answer your question?
Yeah, you answered my question.
Yeah.
Mike, I had a quick question. So if I'm a new user, how do I start with MATLAB?
Okay. Yeah. So if you're a new user, then what we suggest are these things called, my screen sharing again. If you Google MATLAB on-ramp, then you've got a whole bunch of courses here. So if I click on View My Courses, anything with the name on-ramp is freely available to everybody. So these extra courses that don't have on-ramp in the name are for people that have got a MATLAB license as well. But you can click on any one of these on-ramps. It's all free. You don't need a MATLAB license to run an on-ramp. You just need a free MathWorks account. And, if you click on this, for example, I'll be halfway through the course. And what it's doing right now, it's actually setting up a computational environment on AWS. So we use AWS as infrastructure for all of these on-ramps. And these will take you through the basics of using Matlab. So either pure Matlab, or as the one that I'm logging into here now, deep learning with Matlab, image processing, curve fitting, you've got to go all kinds of things. So these on-ramps, they take about 2 hours to work through. When you've finished, don't know why that's taking so long. That's the demo effect, right? This is always fast when you try it yourself, and then when 200 people are watching, it goes slow. That's the rules of the game. But then I'll say, this is running on AWS, so it's your guys' fault, right? Not ours. When you've finished running these courses, you can get a certificate, which, if I go to my LinkedIn profile, where is it? Here we go. There's an example. So there's my credentials showing that I've completed the Simulink on-ramp. So you can add these to your LinkedIn profile and so on. So yeah, that's how I would get started. I would take these on-ramps. And has that has that started? Where was that on-ramp that I started before? Lost it. Okay. Yeah, sorry. Oh no, here it's still setting up. Okay. That's not a good look. I apologize.
Yeah. So Mike, tell us something about this whole SDK for quantum, which you guys started a few years back. Some history around that, and why it is important for the community.
Yeah. Okay. So the quantum add-on then. Me again. Too many clicks to share the screen. So the quantum add-on is, where is it? There. So we call it the Matlab support package for quantum computing. Now, I'll often make a mistake and call it the quantum toolbox. It's not a toolbox, it's a Matlab support package. This is available, if you've got Matlab, then the Matlab support package for quantum computing is available for free. You can download it from this community thing called the File Exchange, and this gives all the details here. So the first version came out not all that long ago. So it was March last year. With the very first version, and then since then we've been, you can see release by release, we've been adding new functionality. So back in July, we added the ability to solve these so-called QUBO problems. We've added extra support for IBM Qiskit and so on and so forth. And the way that I got involved in this is I was asked to write a blog post about it, which meant that first of all I had to install it, because I'm not particularly an expert in quantum computing. I knew a little bit about it because my PhD is in physics, and around about, I guess, 20 years ago, when I was just starting my PhD, we were talking about quantum computing back then, but I think experimentally all we could do was factorize 15 or something like that. It wasn't particularly impressive. But these, so I knew about quantum computing, but hadn't really used it much in anger until fairly recently. But from within MATLAB itself, you can click on this add-ons thing. If I click on here, click on Get Add-ons, then it takes me to the Add-on Explorer. And then from here, I go to the MATLAB support package for quantum computing. And it's essentially the same view that I showed you before on the web browser, but now inside MATLAB. Now I've installed it. So over on the right-hand side here, it says manage it. But if you hadn't installed it, it would just say install. You click on that, it's installed, and you're ready to go. So yeah, that's how you get it installed.
Nice.
Mike, what are some of the use cases or how are customers or users currently using this feature?
So the use cases. Okay, so we, as with pretty much everything that Matlab has, we always have a lot of examples. So if I quantum support and go into our, oh no, our documentation. Here. Okay, if we go to examples here, you see some of the things that that we're starting to build out now. Examples using the add-on that we have. So we've got some very classical stuff, graph coloring with Grover's algorithm, and then some sort of more interesting sounding stuff. We've got one on quantum Monte Carlo simulation here, and you know, protein folding using variational quantum eigensolvers. You know, that's something that I know very little about, but it's got the you know, all of the details here about exactly what the problem is and how you set it up using our add-on and so on and so forth. And for me, I guess the reason why I started to think that Matlab made sense for quantum computing was when I was writing the blog post. So let me find that Matlab quantum blog. So when I was writing the blog post, and we'll walk through this this document in a second, at some point in the documentation, I realized that all of the quantum gates that you have each got a matrix representation. And so when you realize that, then it's like, okay, so as far as I was concerned, then quantum computing was just linear algebra in disguise, or at least that's one way that you could view it. And since one of MathWorks' strengths is linear algebra, it kind of makes sense to me that that you could do quantum computing very effectively in Matlab.
Okay. I have a question around the technical skill I need to start using quantum computing in Matlab.
Okay, that's a good question, and the answer is not much. And I can show you, for example, how you could get started. So here I am inside Matlab here, and I could just open up this this live script. So this is our notebook solution, if you like. And to actually, well, so to get started experimenting with quantum computing, it doesn't take much technical skill, because you can just follow our documentation and run our examples and so on and so forth. But to actually then develop quantum algorithms, that's the complicated part. Does that make sense?
Yes.
Yeah. So for example, I can work through you know, examples and tutorials and so on and so forth. I have never so far programmed any kind of quantum algorithms from scratch myself. But I've been playing with quantum computing now for about a year or so. So I guess it depends. When you say how much skill do you need to do quantum computing, I guess it depends, you know, where are you in that scale of things. If you just want to use quantum computing, then you don't need too much skill. If you want to develop your own quantum algorithms, then you're going to need quite a lot.
So another question will be, why should I think of developing an algorithm? Why?
Why would you develop an algorithm? What, in general, or just for quantum computing?
Just for quantum computing.
Okay.
Yeah.
Okay. So quantum computing, then, it's a fundamentally different way of doing computing, and for the details, like an introduction to quantum computing and what makes it different is way beyond the scope of what we're going to do here. I would suggest you look at Introduction to Quantum Matlab. Let's find you the link. Yeah, this link here. So what will introduce you to exactly what quantum computing is will be this document, and I think it'll be well worth your time going through this. So I'll just add that here. And essentially, quantum algorithms, they offer the promise of being able to solve problems way, 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 way faster than classical computers. And so classical computers meaning your laptop, a high performance computing system, the entire cloud, whatever. In theory, it's possible to solve problems on a quantum computer that would take even the most powerful supercomputer in the world tens of thousands of years to solve. Okay, so that's why people are interested in quantum computing and interested in developing the algorithms, and that's where MATLAB can help you, because you can learn about it and develop algorithms and simulate it and so on and so forth. In practice, it's rather more difficult than that, because it's really difficult to build a big, useful quantum computer that can solve these problems. So we have built, not we, the MathWorks, but humankind have built plenty of quantum computers, of which you provide access to in Amazon Bracket, and you can run all kinds of quantum programs on them. But as of yet, and I'm going to look at Perminder here as the quantum expert, as of yet, I don't think anything has we've never demonstrated any quantum supremacy yet, Perminder. Is that still the case?
No, there are some experiments happening, but to install a production grade application which has a true quantum advantage over classical computer and supercomputer, it is still yet to be deployed. But on the paper, it has been proven. Now, why the algorithm is important is, if you can take an example, right? It's a very basic example. The modern day encryption, the RSA encryption, is based on this mathematical term called like factorization, right? Like it's think of any two numbers, right? You multiply that, you get a bigger number. Now, this is very easy problem in terms of complexity theory to get that bigger number, right? You multiply, you get a bigger number. Now, what if I say like, so start with a number and get those two factors back? That is like very complex problem, and like exponentially very hard problem, NP hard problem in mathematical term. And that is why it forms the basis of the encryption, right? The public and private key, which is this two numbers which multiply to the bigger number, right? And it takes forever for a classical computer to get those factorization done, right? That forms the foundation for the encryption. Now, the quantum computer, because of its inherent principles on superposition, it does this factoring exponentially faster than the classical computer. Okay, and this is proven in the paper by Peter Shor in 1984. So on the paper, it's proven like quantum computer will break the modern day encryption. So your bank accounts encryption, my credit card, everything is up for grab right now, and most of the companies who will break this, thinking of breaking this encryption, is harvesting the code right now, all the stuff right now, and then when quantum computers will be available, they will just break this encryption. Now, all of this is based on that factorization, and we all thought when we were developing this classical side of the encryption schemes, like, oh yeah, we are future proof. It will take classical computer like 100 years to break this, but nonetheless, like if quantum computer becomes available in terms of like its qubit size, like if you're familiar with the bit on the classical, the qubit they need a little bit of maturity in the sense of like to have a quantum advantage. So we are right now in around 500 or so. For less than 1,000, we'll probably need 1 million qubit to break this kind of encryption. Now, that is why people are coming up with an algorithm every week, every day, because that is an area, apart from the encryption, you have quantum chemistry, optimization and all. So every scientist who writes a research paper in archive or a Nature journal, he is either improving the current algorithm like face estimation and things like that, or he's coming up with a brand new algorithm to do the things. Right? Means it is an active area of research. Everybody is talking about Gen AI, training of the foundational model. It takes significant amount of power and compute electricity to train a foundational model and months of time. Okay, so there is an active research going on in the field. Can quantum computer in the future will be able to train this foundational algorithm in lesser time, cost effective, with less data? So that is to answer is a big explanation to the answer. Like, what kind of algorithm? Why I should be thinking about the algorithm? If you are a PhD postdocs, then obviously you're working with a professor to write this algorithm and carry on with your research. If you are a CTO lab sitting somewhere in big bank, you are tasked to use products like Matlab and other scientific software to carry on your experiment and then develop some of the practical algorithm. Right, theory is existing, but then someone has to implement it in a code and all and package this. So there is an active research for writing this Jupyter notebooks code or creating your Python package and all. So opportunity is endless for ranging from a student like grad to the to a 20-year veteran who's used to writing code in C or Python. He has to think about writing quantum algorithm in a new way.
Yeah, exactly. And I mean, some of our customers, for example, as I showed you before, we've got lots of customers in industry, we've got customers in finance and so on. And they're all interested in developing and or using algorithms for quantum that will work on quantum computers. And I think that for the at the moment, I think it's fair to say that most of the existing quantum machines, they just demonstrate they're like a proof of concept. But I think that everybody wants to be ready so that when suitably big quantum computers come, they can run the algorithms that can solve the problems that their industry cares about and that they're ready to go. I think that's where we're at. Should we try a bit of a demo?
Yeah.
Yes, I was going to ask for that. And also, if you can show that, bringing in that algorithm that already exists, where users can just see how to like integrate into that from Matlab, that would be really good.
Okay. So I'll show you a couple of things then. The first one is we'll just walk through what it feels like using the add-on. So okay, so this is the notebook that the blog post was based on. And so I'm actually running inside Matlab now. And anything that's this kind of formatting is code. And the quantum support package for Matlab, it supports two different kinds of quantum computing. And one of them is what's called gate-based quantum computing, in which we make these circuits. So if I run this command here, then what I've just done is is I've created what's called a quantum circuit, and this is one way of programming quantum computers. And so what this does then is I've got these 3 lines. They represent qubits, and then each of the symbols on it are various ways of connecting these qubits together. So what I've done here is I've just created one in this variable called gates, and put that into a quantum circuit, and then plotted the result. So this thing here is called so-called Hadamard gate, and then these things are called C0 gates. And if you're feeling lost and wondering how this actually applies to programming a computer, then yeah, I join you right there. That's how I was feeling when I was putting this blog post together, and actually learning how to program quantum computers. It's like so different from anything that you've done before. It kind of makes your head spin. If you look at tutorials on how to program a quantum computer, they start off with similar material to what I did when I was doing, say, my 3rd year advanced quantum mechanics course. Although these days you can get to what you need to know much more quickly than you did 20 years ago. So anyway, I've created then this quantum circuit. So it's a very simple thing that we can run on a quantum computer. And what I can do then is I can actually simulate this thing. So this then forms like a quantum state that I've got these various properties. So I'm kind of doing quantum mechanics on the computer. And what I did then is I all of these qubits, they can be in any what's called a superposition of states between 0 and 1. And what I've done is I've said, okay, if I start this circuit off, I don't know why the thesaurus keeps opening up. If I start this circuit off with 3 qubits in the 0 state, then what will I end up with? We can turn that into a formula. So this gives us our formula, and at this point, to sort of explain exactly what's going on, I almost need to give you a full course into quantum computing and so on, which not only do I not have time to do, but I'm not really qualified to do. But this is how running the toolbox effectively goes. You can play around with these quantum states, you can do the mathematics on it, you can plot the results of things. And you can say that I'm now going to simulate this system. I'm going to run it 50 times. So when you run a quantum program, the result is it's probabilistic. So in this case, my very simple program will either give this result 0, 0, 0, or with 50% probability, or it will give this result 1, 1, 1 with 50% probability. And that's what the mathematics tells you and the probabilities. But when you actually run them for real, you end up running them hundreds of times to actually then see that. So now I've simulated my 50 quantum measurements of the circuit. And I can then say that when I ran that quantum circuit 100 times, then 46 of the times the result was 0, 0, 0, and 54 of the times the result was 1, 1, 1. Okay, and that's roughly what you'd expect if the probability of getting each state was 50%. So in general, then, doing quantum computing in Matlab using the Matlab toolbox, you've just got all of these basic fundamental tools that allow you to do this. And then if you're anything like me, though, you're then looking at this and thinking, but how on earth does that actually correspond to solving a real problem? Okay, and that's where all the research comes in that Perminder was talking about. And usually, those of us that aren't experts in quantum computing, we need a little bit more help. And Matlab gives you that help as well, because we've got a whole bunch of examples that ship with the product. So one, for example, is given here. So this is one that came with the documentation. We're actually solving a problem in this case, graph coloring with what's almost a traditional algorithm these days on quantum computers called Grover's algorithm. And what this notebook does is it actually walks you through setting up and solving the problem. So, we start off with, we're going to create a graph that's got 4 nodes and 4 edges that are connecting them. And then you can go through this, and it explains all of the mathematics and quantum mechanics and so on that you need to do to be able to solve this problem using a quantum system. And you can see that it's fairly involved, right? When you read this, it gets pretty complex pretty fast, but you don't necessarily need to know the details if all you want to do is run through it, get to the end, and get the problem solved. But all of the mathematical details are here for you, okay? In this particular example here, and in all the examples that we ship with Matlab. So if you go to the documentation, for example, and we search for quantum in here, then you get, we have several examples that will go through all of these in a very similar way. So here then, this is from the documentation, I can then open that live script. It opens the code directly into Matlab. And now I've got a different problem that I can solve with the quantum toolbox. And the reason why I'm not going into any detail with these is you can see that there's a lot of mathematics going on here, right? And it takes a long time to sort of like figure out and get your head around what the mathematics means and how you can apply it to your own problems and so on and so forth. And that's why Matlab ships with all of the examples, so you can take the time to do that. I'm not sure how much more of a demo I should show here, because it is pretty much just like running through the code and looking at the mathematics and so on and so forth. And I'm not sure that that's a particularly good use of the time. What do you guys think?
Do you have like a very common problem that everybody, like people can relate to on that you can show us on quantum computing?
Yeah. So that's a good question. Let me think. Excuse me, like I say, not used to having such a small screen. Traveling Kubo. Okay, let's look at this one. And yeah. So for some reason, I can't see the open this in Matlab. Normally, there would be a open this in Matlab, open the live script in Matlab, but it's not there. So I'll, rather than run the code, then I'll just step through it. So here's an example that you can imagine has got a direct real world application. So it's called the capacitated vehicle routing problem, and as it says here, it's a combination of the so-called knapsack problem and traveling salesman problem. So you've got some kind of a base of operations in the center here, and maybe you've got a fleet of electric cars where each electric car has got a certain range before it has to return back to base to be charged, and you want to visit every single one of the sites in as smaller a route as possible. Okay, and you've got a limited number of cars. Each car has got a limited range, and so the question is then how do you solve this problem? So this is an example of the kind of thing that you can use quantum computing to solve. But in this particular case, as you're setting up the problem, and you go through this documentation example and run the code, but in this case, it's been run for us. As you're working through it, you start to get to a point where, so far we're just it's just working through the code to set the problem up. At the point where we actually come to solve it, what we do here is we don't use that version of quantum computing that I showed you before, which was the gate-based quantum computing. Traveling salesman problems and things like it, like this capacitated version, we solve them by converting them to something called a cubo problem, which is quadratically, help me out, Perminder, what does cubo stand for?
Unconstrained binary optimization.
That's the one. Yes, thank you. So cubo problems, they're essentially a kind of optimization problem that if you refactor your code such that it's a cubo problem, then it's very straightforward to map it onto a certain types of quantum architectures. Okay, and so the rest of this example then will do exactly that. It explains how to convert this initial problem to a cubo problem, and then we can send that to a quantum solver for solution. In this case, it comes up with a solution here. So there you've got your depot, and this is the eventual solution that it comes up with. One of the problems that we have at the moment is that we can solve cubo problems in MATLAB classically using something called a taboo algorithm, TABU. But we don't have any direct way of running the cubo problems on quantum hardware. And so for that, what you can use, though, if you do want to run cubo problems on quantum hardware, then you can use a product called StrangeWorks StrangeWorks MATLAB. That would do. So there's an organization called StrangeWorks that have built something that builds on top of our MATLAB quantum computing package, and this will allow you then to send that cubo problem to physical hardware in various places. And actually, I suggest that you guys maybe consider having StrangeWorks on your show in the future, because they're a really cool platform.
Yeah, StrangeWorks is one of our quantum partner too, right? They have a backstage program, so we have been heavily involved with them from last few years.
Yeah.
Include them, maybe three-way. But yeah, I mean, carrying on that conversation with traveling salesman problem, right? Like, means think of the use case, like even our own Amazon last mile delivery package, right? The Rivian vehicle, electric van going around. You can think like that. In autonomous vehicle side, routing of the electric vehicle, right? So these are tough, mathematically very complex problem. Scheduling of the flights, or the workforce scheduling, like nurses in the hospital. So those all comes under the cubo setting. And then you set up your objective function. Then you put up a constraint by saying, like, because like nurse 1 and nurse 3 is only supposed to work, but nurse 2 and 4 and 5 supposed to work. And some nurses will work on this day, but not that day. But then there is only demand of this much on this day. So those, when you start adding those constraints to these objective functions, it becomes very, very complex, right? And then this is currently being solved by classical computer. But the promise is, like, once we have the quantum hardware, this can be solved in a polynomial time, right? Not in exponentially higher, but like a polynomial time. So that is why we call it as like max. And various form of this driving salesman is very generic age-old problem. But then you put a solution like vehicle routing or last mile package delivery, things like that on top of it. And even in some cases like max cut, which Mike was mentioning, like max cut algorithms are also used in a map if you position like your Starbucks location. I'm just saying Starbucks location, it can be Panera too. But if you are mapping a strategy like where to place those location and which location it should not be connected with that. So max cut is that sort of like a scripting where you have edges and the nodes, and then you are trying to cut it those with a maximum maximum cut. So all of these are like a mathematical problem in the table setting.
Mike, I had a quick question on the cost that's associated. I think the examples that you showed were great, and there's so many example notebooks. So if I'm a user and I just want to run through some of the example notebooks, then how would I know how much it would cost me? Can I just go and experiment?
Yeah, okay, so good question. So when you're doing everything that I've shown you so far, you're just running in Matlab. So Matlab is simulating a quantum computer. Okay. At no point yet have we actually run anything on a quantum computer. And maybe actually that's something I can very briefly show you now, and because then it goes straight into the cost. Okay. So if I go back to sharing my screen and we go back to Matlab. Okay. So this was the notebook that I was showing earlier on that had the very simple, this quantum system here. Okay. So don't worry so much, about what this is doing. It's so simple. It's
share.
Sorry?
Yeah, now I see.
You can see?
Yeah, I can.
Yep. Okay, good. Yeah, so, don't worry so much about what problem this is solving. It's not really solving a problem. It's just a very simple quantum program, something that we can run. We can simulate how it should behave on a quantum machine, and then we can run it on a real quantum machine and see how we actually do. So this was the system that we were looking at. And when you simulate it then, so we're going to run that quantum circuit 100 times, and we can see that we get these results here. 46 of the times the result was 0, and 54 of the times the result was 1, 1, 1. Okay, so we were essentially flipping a coin, I guess. If we then skip through all of this this chit chat in the article here, and we get straight through to this point here, what we did there was a total simulation. It didn't cost anything. It was just running on my laptop. And it was completely simulated. What we can do, though, and this is where I guess the partnership with you guys comes in, is that with a little bit of extra code and configuration, and I'm not going to show you the configuration because it's not the most interesting thing to show, but it's relatively straightforward. If you've used Amazon before, it's not too difficult. I just followed the instructions. I didn't have any special help, and I got there fine. But then once you've done the setup, then it looks like this piece of code here. So if I just run this, then what I've done, this first command here has got, it's loading up all of my credentials and so on that allow me to access AWS. And then what I'm doing here then is I'm accessing the Amazon bracket. Do you guys say it like that, bracket, or do you just say bracket? How do you?
We say bracket.
Bracket. Okay. I'm just thinking back to my old physics lessons, and I can hear my PhD supervisor saying bracket, which is why I think I did it. I say it that way. So if we take a look at where is too many, classical thing of too many tabs open, right? Here we go. Here's the Amazon Bracket service. And you guys are offering physical, real quantum computers from various providers around the world, right? And when I wrote the blog post and I did the first simulation, I used this machine here, a Rigetti, the Aspen M3, which had 79 qubits and superconducting QPU. And I chose it simply because it sounded cool, if I'm being honest. But for whatever reason, that's offline at the moment. It's not available. So the one I'm connected to now is this IQM Garnet. You know, so we can see here that it's 20 qubits. It's available, it looks like, for the next 18 hours. And if I click on this, then I get various bits of information about it. So I get the name of it, which helps me access it in Matlab. So I get the information I need for Matlab from here. And then it's got the various details about the physical machine here. So we can see, for example, that it's actually located in Finland. And there's some information about the physics up here. It's a high fidelity 20 qubit QPU, quantum processing unit, based on superconducting Trasmon qubits. It sounds like something straight out of Star Trek to me, to be perfectly honest. And when you talk about cost, you get this information here. So we can see then that the cost we're interested in is this stuff here, and it's 30 cents per task. Okay, and we'll talk about what that is in a second, plus 0.00145 cents, so that's not very much at all, per shot. And so let's go back to Matlab and talk about what that means. I keep clicking on the wrong thing in Matlab because I want to go here. Okay, so I'm connected to my device, and I can inside Matlab I can fetch details about the device. So we get an awful lot of information about what this thing can do. We'll not dig into those details there. It's very similar to what you get on the website. And what we're going to do is I'm going to run that circuit that we created at the beginning of the blog post. So this thing here, we're going to run it on the device. So I've created a task. So that's the thing that costs 30 cents. Okay. So by asking to run, I'm asking to run this circuit C. So this circuit up here, I've called C, it's stored in the variable C. I want to run this circuit on the device that I've created there. Okay. So running that task, when it does run, so at the moment it's queued, running that task will cost me 30 cents. So at this point, I've already, I don't know if the cost kicks in when it's queued or when it's ran. I guess when it's run, right, Perminder?
Yeah.
Yeah. So when that runs, it will cost me 30 cents is the base. However, by default, when you ask Matlab to run on a quantum circuit, if you remember going back up to here, when I was doing the simulation, actually there's a typo there. There we go. When I was doing the simulation, I said I want to run the circuit 100 times in simulation. And that's to allow us to give the statistics, because you remember that these quantum systems, they're probabilistic. So, you know, this one half of the time it's going to give me 0, and the other half of the time it's going to give me 1, 1, 1. Okay. So in order to get the statistics, in many real problems, you're going to have much more complex statistics. So you have to run very many times so you can see the probabilities pan out. So if you just run once, so-called shot, and run your circuit once, then the result that it gives you doesn't give you too much information. It's only when you run it a lot of times, 100, 1,000 or whatever, that you start to get more meaningful information. And so going back down to here, then this tasks cost me 30 cents, and then it's going to cost me 100 because that's the default number. I could have changed that in this run command, but I didn't. It's going to run 100 shots, and since you asked about cost, the cost then it's 100 times that thing there. So this whole experiment is going to cost me what, 31.4 cents.
Yeah.
I think that that's sufficiently small that I won't bother submitting a expenses claims to you guys, right? Just we can deal with that. So if you're just playing around with these things, then it's I think it's pretty cheap. But that's also why you do so much in simulation before you go anywhere near the quantum machine. Because if your algorithm doesn't work in simulation, there's no chance at all that it's going to work on a real machine. So you get it working in simulation first, and then you go to the real machine. Yesterday, Perminder, when I ran on this system, it was in the queue for a long time. Yeah, and indeed now it's still, I guess because there's a few systems offline on Bracket, then this system's really overused, right? So I'm going to be in the queue for a while.
Yeah, and then I think some of you and then people in the audience know, like, you know, the quantum compute is a scarce resource. You know, it's like a premium in terms of like in need and availability and all that, right? That is why when you showed in a console, like some of the devices were online, offline, and all. So all of these QPUs, which are hosted in AWS third-party data center by these partners, quantum partners of ours, they are available for few hours. Now, what people generally do is like they submit the task and it goes into a queue, right? And whenever the system comes online, it executes the task and then it gives the result back. Now, that is the standard way of doing, like sort of like on demand. And I think this may be a good point for me to share my slide, because what we did at reInvent, let me share my slide and just cover the things which I wanted to cover. Share a screen. And so do you guys see something on my screen which says called like bracket direct? Those who are familiar with the AWS language, like on demand, reserve instances and all. So what we did reInvent 2023 was release something called like bracket direct. Under bracket direct, you can actually reserve a time where you can run your circuit without waiting in that queue, which is sort of like a general queue, right? If you're a research scientist or you're part of a CTO lab team, you know for sure you will be running this circuit Friday 10 to 11, right? So you can go ahead and reserve that particular device, and submit the request there, and then our team will be notified, and then it will be available. The compute is available for you exclusively. That is what this program so that is one way to circumvent the queue problem, right? We could use the, but nonetheless, since it's a premium, there is like a premium price for that, right? Like there is a price tag to that, and this is currently available for Garnet device. The Garnet device which Mike you were showing, it is available from our partner from Finland, IQM. And the way to reserve is like you have something called like on the top, like reserve device, and you can reserve either Garnet or in this case IonQ, so device like that. And apart from that, what we also launched at reInvent was like some of this hardwares, they're like a different modality of the hardware, a little bit different in each of the case. Like some of them are superconducting, some of them are Rydberg or trapped ion based system. So we also launched a one-on-one consulting service with some of this hardware partner. So once you are in a Matlab, you're trying to explore something, you're trying to use the Garnet device, everything seems to be okay, but still it's not running, right? You're facing some developer sort of like issue. So this is another way where we can connect with those customers, can directly connect with the with Quera or Rigetti or IonQ SMEs, and where they can get on a call and troubleshoot. So you can submit like that. Apart from that, our own scientists and the engineering team has a bracket officer. You can actually schedule a time with them to speak. So schedule a time for the hardware, schedule a time for the consulting offer, like a software services offer, both available. The device which you are showing, right, and this was, I was planning to show, but since you covered, right, is 20 qubit system. This is first machine in the, after OQC, the first machine in EU right now. It's hosted on the Stockholm region of AWS there. Available both on demand and direct. This is some of the time which, where it is available Monday to Wednesday, 8 o'clock, and then Thursday to Friday, 1 o'clock UTC time. And this is based on it is high connectivity, and what the term we use in the community is like it's sort of like a square lattice. Now all of these devices, different modality, will have some pro and con, right? Like some of them are more noisy, some of them are more connected, and things like that. But nonetheless, this has high connectivity, 20 qubit machine, square lattice, and there are like 1Q and a 2Q time, like 99.992 for 1 and 2Q. This is the QR code, and where we have actually launched a blog. So if you go to the AWS blog, it did explain in detail like how to use this machine, and there is an example code. These are other QR code, like the black bracket algorithm library we have, which we can be used. But there is one very important thing. I see, we have enough literature on the AWS blog and press releases about what MEM bracket is. But if someone wants to really understand in and out of bracket, we actually launched at reInvent a badge program. So mostly on all AWS services like machine learning, we will have this certification, like machine learning certification, database certification. At least for the quantum, right now we don't have a certification, but this is a badge program, which is like assessment. With that, what you have to do is like go to Skill Builder, attend this training for free, which is, and then after attending the training, you go and write a assessment, 50 questions, and you get 40 of them right, 80% of them are right. So you get a bracket badge, and then, from there on, you can brag in your community, in and out of bracket, quantum computing service of Amazon. So this is a nice intro to that, and there is a blog there too, which can be leveraged to know how this bracket badge program works. So that is, I thought, like, since you're mentioning Garnet, you were mentioning like you pushed a task yesterday, still waiting in the queue, that is fine. That is what I and you will do, right? But if it's a corporate or some national research lab, they know for sure they will run this algorithm. They can use the bracket direct program. Yeah.
Okay. Thank you. I have a question for Mike. I wanted to ask what are the biggest challenges when it comes to adoption of quantum computing? But before you get to that, I want to kind of welcome people who were not with us from the beginning. Welcome everyone to this episode of Howdy Partner. This is a weekly series where we bring on our AWS partners to come and highlight like products or solutions they have on AWS. And today we have MathWorks talking about Matlab and different quantum computing use cases, and also how you can leverage Matlab to run your quantum computing workload. So Mike, I want to hand over to you to tell us what are the challenges you're seeing right now when it comes to adoption of quantum computing.
For me, I think the biggest difficulty is figuring out how to map your problem to a quantum machine, to a quantum algorithm, because it's such a different way of thinking, of programming. It's like I've been programming for many years. I'm trying to think of a number now. More than 30 years I've been programming, and I feel like I know how to. If you were to tell me what your business problem was or what your research problem was, I could start to leverage all of that experience pretty easily. Not easily, but I know how to do it to start solving your problem. When it comes to if you were to then say, okay, now I want a quantum algorithm, I feel like all of that experience doesn't mean as much, because I'm having to go back to school myself to understand how all of this works. And would you agree with that, Perminder, that it's really difficult to go from a classical programmer to a quantum programmer?
It depends. I think biggest thing in this is the attitude and the interest. I did a transition, right? I graduated in my telecommunication engineering like 2001. So it was almost like after 20 years, I did a switch on the job. So I did my master from Madrid University in quantum computing for 2 years. And it takes a while to understand what is happening, okay? And there is various way to approach this. There's, of course, there is hardware getting built. We need the physicists, PhDs in the electrical engineering and all that, right? But then there is a mathematical way to approach this to understand, like in the end, like what is happening behind the scenes, matrix multiplication and things like that, right? So I think I fit in that category because I come from the software background, right? I will be building the application algorithm, not the quantum hardware, but software, right? So building a quantum hardware is a very challenging thing, and there is a special team, special PhD. They are sitting at least on our side in Amazon. Like we are building our own superconducting quantum computer at Caltech, and there is like 100+ people sitting there and building this, solving this massive engineering problems, the scalability, the error, and all that, right? But at the same time, there is an equally important thing on the software side. People need to come up with the actual practical implementation of the algorithm, which is written on the paper. Right now, we can't deploy production grade problem, but we can start with a toy problem, right? The vehicle route problem, which you talked about, at least if 8 to 9 qubit small size problem, you can simulate that. And at least in my case, like, I took up as a part of my thesis, the master thesis project, right? I took up a neural network problem, which was time series problem. And I approach it through the random forest on the classical side and neural network, and then support vector regression on the quantum side, right? And then best way to learn is different for different people. If you are strong in the mathematical side, you can approach it like that, right? You don't need to know anything on the physics. But if you're interested in building hardware, then of course you need to have some understanding of the quantum material and how they work at the physics level. But nonetheless, opportunities everywhere, okay? But it needs a different thought process, okay? First, you have to unlearn some of the things. You probably have to read or watch some YouTube video probably twice, thrice, then only it will start making sense. Because you will have the algorithm and then you will have the data, right? You have to encode the data in the quantum state. That takes a little bit of understanding how you will encode that data. Then you have to apply like operation, what you will perform on those qubit with using that gate, which we were talking about, Hadamard gate, control NOT. And if we remember some of those mathematical terms, like remember like OR gate, NOT gate, XOR gate, remember that truth table. So some of those also come into a play. So you will naturally, if you are strong in that area, you'll start applying that analogy into the quantum. First month, you will probably forget everything what you heard. Second month, you'll start making some sense. But it will take probably a year or two to understand what the heck really is happening, where you start coding. Actually, you start coding, opening up the Matlab or any other Jupyter notebook and start coding. So different people take different route, but I took my own route through the mathematics. But yeah.
I mean, I think, so at MathWorks then are one of the approaches that we're taking to help on board everybody is just to have as many examples in different domains as possible. So actually showing how to solve various problems using either gate-based quantum computing or the Kubo formulation or whatever. We've actually got people want to contribute to it as well, or see what we've done so far. We've got an open source. Let me just we've got an open source set of examples for quantum computing. with MATLAB on top of what we have in the documentation. So again, if I then share my screen, the link will be coming up in a second. But here, so for example, MathWorks got a reasonably big GitHub presence these days, and this thing here, which it shows also how to, there's plenty of examples now to run the quantum circuit on AWS and IBM hardware. But inside here, we've got like some other examples on how to do things like do some machine learning, building various classifiers using quantum computing. So classifying credit ratings, for example, with classical and quantum models. Or we've got portfolio optimization, which was based on a paper here. So so yeah, portfolio optimization uses that Kubo formulation that I was talking about before. So I think this is one of our approaches to helping people get started with quantum computing. While you can start from the very foundations and learning how to build up the gates and so on and so forth, we're also building examples, and from the examples we'll build functions that can just be deployed on the quantum hardware and allow people to solve problems and just be thinking more in problem space rather than in the details of quantum computing. Does that make sense?
Okay.
Mike? Yeah, sorry. Go ahead, Nneoma.
Okay. I have a question regarding, generative AI, quantum computing. Where does, with the whole, trend, what is the trend going to when it comes to quantum computing? Because at the very basic, we know that quantum computing is just to help with all those algorithms that classical computers can, it's either a long can't even compute in a classical computer. So I want to know, what are the future trends? What are you seeing in the quantum computing field?
So the right now in the customer landscape, right, we are hearing a lot of noise and trend in using specifically, these three things, right? HPC, a lot of times like HPC and hybrid computing with quantum is coming into our conversation. And then somehow Gen AI is also getting involved into here. There is an interesting paper. I have to go and search for that, but like a paper written by Los Alamos Lab in using the quantum in the Gen AI transformation, the training of the foundational model using the transformer model. Right? So there is but this is an active area of research. But at least on these combining the supercomputer and quantum computer, there is an interesting work some of the companies have already done it. Okay, if you're familiar with the whole machine learning using the GPU, you set your problem statement and all in the CPU, right? And then when you need to train a particular algorithm, you hand it over to the GPU. And GPU does its job. If it is a feed-forward network, it needs it gets the result, and then you use the backward propagation, fine-tune the weights, and then you get the run again, and then you get the result, and then you measure whether you're close or not using various technique there. So you come up with the most optimized solution. Now, if you picture that, you just replace the GPU part with the quantum processor. That is where I think the neural network in the quantum way is possible. Okay, and I have actually done master's thesis, ran the experiment on that sense, like predicting the electricity pricing and all that. So there is a future for that. Now, on the NLP side, on the natural language processing side, it is still a lot of research paper is being written. Okay, and I'm sure at this point people are actively looking to augment the training or the foundational model, or whether it's fine-tuning using the quantum processor, for sure. But it will be a little bit of like a hybrid in a sense, because quantum computers are a purpose. It has a purpose for specific use cases. It's not idle, or it's not going to be used to run a database or run a website. It functions like the way GPU fits into this machine learning. Likewise, quantum processor also fits into quantum machine learning, whether it is drug discovery or whether it's optimization task like vehicle routing. So in that sense, like there is a trend. But will someone come up with a new transformer model where they train the foundational model within a 2-3 days, and instead of like companies running it forever, like 3 months, and then large compute, and they use a lot of energy and then processing power? Can someone come up with? Answer is yes, probably someone will come up, right? That is why this is in a active area of research, and then if you or I can get that algorithm or discover, we'll be $1 billion company, right?
So one more question I have is, when it comes to, you talked about the different industries in electricity, which industry do you think would benefit most with this trend you talked about?
Now, see, we at AWS generally are very conservative, right? We don't commit on the timeline of the supremacy, quantum supremacy, and then the which industry will benefit. But many times, like we get the management consulting report, whether it is Gartner or McKinsey or IDC, they give a fair bit of idea like which industry will benefit from it. I think there is a report by McKinsey in April, right? They showed us like which sector will be maximum impacted. And I think if I remember, it was like financial, the life science drug discovery, and then the automotive and manufacturing sort of. Okay, so it has some dollar value assigned to those, and they were also bifurcated according to the line of business, like the electric vehicles, battery, so that one, the whole FSI, the stock portfolio, or Monte Carlo simulation of the return of investment on the portfolio. Those were being discussed there. Now, what will happen for sure? I don't know if I can precisely say like this industry will take first benefit first. I think all of this industry will benefit if they fall into either machine learning or optimization, like logistics, supply chain, or like quantum chemistry, like drug discovery and all. But nonetheless, this is the part of the commercial side, right? But remember, I told you guys about the encryption, the security, and all that. All of the classical resources are at risk right now on the paper, for at least, right? And then the national government agency, the US or Canada or China or India, everyone is racing to get the quantum computer built. It's like it's sort of like a geopolitical race, like after the space race and then the space race and the atomic race, right? Like this is probably that sort of like thing going on. So every country is also trying to warm up internally the various national labs they have, like Los Alamos or Oronel, right? You set up like in Chicago, University of Chicago, quantum initiative, and Boulder too in Colorado, and same thing is happening in UK or EMEA. So security is probably getting funded too, because governments are directly involved, right? They are giving out the grant and all that. So now, which industry will get impacted? Of course, banking will get affected, credit cards, and things like that, right? So money-wise, and then.
Yeah, I mean, for me, it's interesting, the industries that you mentioned, because I think as you were talking, like finance and automotive and pharmaceuticals and so on, I was thinking, oh, that's our customer, and we have an example for that, and that industry is our customer, and we have an example for that as well. And so I think MathWorks is thinking in a similar line, in that we kind of see industries that could possibly benefit from this stuff, and so we're interacting with customers in those industries, and we're providing examples and so on. But yeah, like you were saying, I think it's difficult to predict at this stage which ones are really going to be the winners. And I guess it's, when the quantum hardware comes that really does give the advantage to using quantum algorithms as opposed to using traditional HPC.
So yeah, I shared a slide, right? This comes from the BCG's report from 2021. If you see like the simulation, which is also called as quantum chemistry, right? Like, so things like drug discovery or catalyst design, right? Derivative price and finance, they will get impacted. And then you have some optimization, like whether it's portfolio optimization or logistic network optimization or aerospace route optimization. Those also will get impacted. Now this data is from 2021, like machine learning, whether it's automotive or finance or cryptography, the security side of the house. But numbers are numbers can change. But these are some of the reports. There is a one by McKinsey too. So now, end of the day, we can actually debate like, okay, security will take more, but there is an opportunity everywhere. But it's difficult to predict like for precisely what will happen.
Okay, thank you, Perminder and Mike, for that. And I just have 2 more questions in my bucket. I don't know if any other person has more. One is, how has it been partnering with AWS, being being part of the AWS partner network? And then the last question would be, what is the future looking like for MathWorks? What are you doing? What are you working on? If you can tell us, if you can share, that's fine. If you can, that's okay too. So we want to know what MathWorks has in the works.
Okay. So the first question, what it's like to partner with AWS, I'm not the best person to answer that, actually, because I don't directly deal with the partnership. The other people in MathWorks that do that. So, for example, Perminder, I guess you talked to Sahini quite a bit, right, on the quantum side?
Yeah. So means Matlab is our both customer and partner.
Yeah, right? Exactly. So I can speak sort of generally that because we interact with AWS a lot, I work with solutions architects and all kinds of people at AWS, and it's always quite a pleasure to do so. I've have plenty of people in AWS that I now consider my friends because I've worked with them long enough, and whenever I go to conferences like SC, we usually catch up and go for a beer or a coffee or whatever. So yeah, it's a great organization to be both a partner and a customer of. In terms of what MathWorks is up to, yeah, we have, MathWorks tends to have a policy of not talking too much about what we hope to do. And this partly comes from, we never want to be accused of vaporware, because sometimes it can take such a long time to bring something to fruition that people are saying, yeah, you said you would get this done by this date. You didn't. You've let me down. I was dependent. You know what I mean. And we don't want to do that too much. What I can tell you is that MathWorks has a new release every 6 months. We've been having this 6-monthly cadence now since 2006. So it's for any given year. So now it's 2024. So we have MATLAB 2024A, MATLAB 2024B. The only difference between the two of them is that one is released in March and the other is released in September. Some people seem to think that, I don't know, we hear some strange things from people. They'll say, oh yeah, well, I know you've just released the A version, but we'll wait for the B version because that's where that's the bug fixed version. No, they're all equally, sort of high quality. And the only difference between A and B is that one is released in March and the other is released in September. So to give you an example then of what happens when we release these things, if I share my screen, it's another blog post. I'm afraid I am the Matlab blogger. I'm going to be using blog posts a lot. So you can see that some of the stuff that we came out with back in March, we're focusing in some instances very much on our core. So solving ODEs, for example, we've got a whole new framework for solving ordinary differential equations, and that's been extremely popular among our user base. I had a lot of feedback on that, and there's going to be, you can just see there's going to be more work done on that because that's kind of the direction we're going into. We're always developing the language more. So the intersection between MATLAB and Python is getting we work with Python better every release. So something I'll be writing about very soon actually is about, for example, how you can automatically convert between pandas data frames, so Python pandas data frames and MATLAB tables. And MATLAB's always getting faster and so on and so forth. So that's MATLAB itself. And then a big part of our ecosystem are these toolboxes, which are the very specialized stuff. So we're always coming up with new toolboxes in new domains and so on and so forth. I can't really talk about what's coming. I just have to wait and see. But there's plenty coming that is the deep industry verticals, so to speak. But I kind of want to just sort of like leave you with this this image here. So this is from one of our products. Where if you have a MATLAB campus-wide license or an enterprise license or whatever, you'll have access to all of this. So these animations here are all full physical simulations. In many cases, so this one with automated driving, that's got neural networks behind it, and we're actually simulating putting the algorithm into real things into a full 3D environment. So this is what MATLAB can look like today. And I would just say that to keep up with what we're doing, feel free to follow the MATLAB blog and other resources like it, where I'll be keeping you up to date. But yeah, we're there on the front of things like quantum computing and machine learning. And you mentioned generative AI. Something else we did very recently was we've now got a. Let me see if I can get it up fast enough. I've not got my. Where is it? So we have a. We have a. What is it that OpenAI call them? We have a thing. It's a MATLAB GPT essentially. So if you go into OpenAI's marketplace, then you have something in there that is specifically tailored to MATLAB, and it also uses RAG methods, so retrieval augmented. What's the G stand for in generation? Generation. We have one of those that's specifically for MATLAB. So now you've got a tailored version of ChatGPT that can also search the MATLAB documentation and so on and so forth. So yeah, we've got a lot of things going on in lots of different areas, and I think if anybody wants to reach out and have a chat, then they can find me on LinkedIn or reach out to anybody on MathWorks. There we go.
Hey, I'm gonna share your LinkedIn in the chat, so anyone who's interested can reach out to Mike. Perminder, do you have any more questions that you want to ask Kruthi?
I think if there are further questions, you can reach out to me from AWS side, or you have a very targeted question on how to start using Matlab with Quantum SDK as the plugin which we showed for enterprise, and want to have one-on-ones sort of like call between me and Mike. We can also arrange that, right? So stay tuned, experiment, learn, and there is an opportunity for everyone. And yeah, thanks for listening to us.
Okay.
Yeah.
Mike, is that? Sorry, Kruthi, you want to
Yeah,
say something?
I think this was a really interesting session. I'd like to thank Mike for explaining all of MathWorks and quantum computing today. And yeah, we also have a survey for the audience. So if you can, I'll paste that in the chat. If you can fill out the survey, that would be great.
Okay. Yeah, getting the survey. Okay. Here is a survey. Please help us fill it out and give us feedback on something you would like to, topics that you want to talk about, or partners we should bring on the show. Thank you so much. Mike, is there anything that you wanted to touch on that we didn't get to ask questions, or you didn't talk about it?
No, I think this has been great. Thank you so much, everyone. Yeah.
Okay. Thank you so much to our audience for staying with us for almost 2 hours. That's a long time. Thank you for staying with us and engaging. Thank you, Mike, for all the wisdom you shared regarding quantum computing and MATLabs and MathWorks and what they are doing with MATLab. Thank you, Perminder, for your insights. Then Kruthi for your support. So with that, we've come to the end of the show. Join us next week as we bring on another partner who will talk about automating developer tools. So enjoy the rest of your day. Bye.
Cool. Thank you. See you guys. Bye-bye.
Bye.